Crash Course Instrumentation, Episode 33, Voltage, Current, and Resistance, a Fluid Analogy. Welcome to the first episode in our new series on Ohm's Law and Joule's Law. In this episode, we're diving into the core electrical quantities, voltage, current, and resistance, using something almost everyone understands. Plumbing. The water analogy, think of voltage like water pressure. It's the force that pushes water through a pipe. In an electrical circuit, voltage is the electromotive force that pushes electrons through a conductor. It represents potential energy per unit charge and is measured in volts, V. The higher the voltage, the greater the potential to do work. Current is like the flow rate, how much water moves through the pipe in a given time. In electrical terms, it's the rate of flow of electric charge, measured in amperes, A. 1 ampere equals 1 coulomb of charge passing a point per second. Current tells us how many electrons are moving. Resistance is the narrowness or friction in the pipe. A narrow pipe restricts water flow. Similarly, electrical resistance slows down the flow of current. It's measured in ohms, O, and depends on material, temperature, length, and cross-sectional area of the conductor. Copper has low resistance. Rubber has high resistance. Electric circuits versus hydraulic circuits. In a closed-loop water system, water must flow in a complete circle. In an electrical loop, charge must do the same, move continuously from source to load and back. Both systems demonstrate how energy is transferred from a source to perform useful work, like turning a motor or lighting a bulb. Quantifying the flow. We define voltage in volts, V. The push or potential difference. Current in amperes, A. The rate of flow of charge. Resistance in ohms, O. The opposition to current flow. Ohm's law ties them together. V als I x R. This means more voltage results in more current if resistance is constant. More resistance means less current if voltage is constant. Why this matters. Understanding this model helps you diagnose problems in control loops, read sensor behavior in analog circuits, predict power draw and voltage drops across components, build intuition for designing circuits, troubleshooting loops, and protecting devices from overcurrent or overheating. A thought experiment. Imagine a pressurized water tank connected to a long hose. If the hose is wide, water gushes out. This is like low resistance, high current. If the hose is narrow or kinked, the water flow slows. This is high resistance, low current. Same principle applies to electricity. Same goes for voltage. More pressure equals more push, until resistance pushes back. That interplay defines how real-world electrical systems behave. Historical fun fact. The term volt is named after Alessandro Volta, who invented the first true battery in 1800, the voltaic pile. The ampere is named for André-Marie Ampere, who formulated the laws of electrodynamics. And of course, the ohm comes from Georg Simon Ohm, who discovered the proportionality between voltage, current, and resistance. Even though these men worked in the 1800s, their names are spoken daily in labs, classrooms, and work sites around the globe. Coming up next. In Episode 34, we'll go hands-on with real batteries, resistors, and multimeter measurements. You'll see how Ohm's law plays out in real circuits. Like, share, and subscribe to stay current with Crash Course Instrumentation.